Yanfei is from Argonne National Labs. He is here to talk about OFI and its support in MPICH. He's an assistant computer scientist, at Argonne National Laboratories. His work mainly focuses on research and development of MPICH and a high-performance MPI implementation. So it's my pleasure to welcome you to OFA workshop, and the stage is yours now.
All right, thank you. Hi, everyone. My name is Yanfei Guo. I work at Argonne. I lead the program model and runtime system group now, and I'm also the lead PI of the ECP exascale MPI project. So today I'm just want to talk about the status of our support and usage of LibFabrics in MPICH. Next, please. So I'm first going to talk about what is MPICH and why we choose OFI in the development of our library, and then we'll talk about what are the major changes that we bring in the recent version, especially with the support of GPU, and then I'll finish with some future plans and directions. And next slide, please. So MPICH, as you may or may not be aware of, is a high-performance portable open source implementation of the MPI. So it provides all the functionality that MPI defines as a standard, including the upcoming MPI 4.0, and that's been mainly developed by Argonne and in collaboration with UIUC and many close collaborators, including Intel, Korean Knox, and basically many institutions. So we have a currently stable release of version 3.4, and just earlier, a couple of weeks ago, we have released the first alpha version for the 4.0 series. And you can find more information at the www.mpich.org. And next, please. So our model is what we generally refers as a MPICH ecosystem. That we have MPICH, the open source library, and we have many vendor partners and collaborators that take our open source code, which contains the general optimization and implementation for the MPI, and add their specific optimization targeting their own hardware and release as their vendor's MPI version. And on top of that, we have close collaborations with the tools community and also the mathematics library and other library community to provide essentially a better support to the greater scientific computing community. Next, please. Okay, so a couple of years ago, when we looking at our directions of the new MPICH development, we choose to build our library on top of OFI LibFabrics, mainly because we're a small team compared to all our vendor partners, right? So we really wanted to focus on the general implementation and general optimization that can be applied to almost all scenarios. But at the same time, we recognize that our end user and really need optimized performance for their own machines, their targeted system. So using OFI provides with us the opportunity that allow the vendors to put their optimizations inside OFI. So basically, we're relying on the vendors supporting in OFI to for the optimized performance on machine. And on our side, we will only have to focus on generalizer support. So that apart from that, it also brings some benefits, including having a fully functional socket provider, which we no longer have to maintain our own version of TCP implementation for the MPI and all kind of that.
Hey, Yanfei,
yes.
Can you please get closer to your microphone? Looks like the voice is, I mean, we can hear you, but it's not as loud. So
okay. Let me try to bring the microphone. How about now?
Oh, this is much better. Thank you.
Okay. So I'm too far away from my webcam. Okay, next slide, please. Okay, so our latest stable release, MPICH CH4, has some major change compared to the existing one. So the first thing is we introduced this what we call a CH4 device, which we'll explain later what CH4 is. The CH4 device basically provides the low-level functionality for the MPI. So in the version 3.4, that became the default device and replaced the old CH3 device. So the main objective of having CH4 device is one is to have really low overhead and really lightweight implementation, so that for communications that really optimized by the OFI and the lower communication library, we don't want to add too much overhead on it. So we want to really essentially just passing the information down to the OFI for communication, that is. And it's also relying on OFI for hardware tech matching and all that stuff. So as you can see on the top right figure, just with this lightweight implementation alone, we'll be able to improve the performance of an actual application. This is NEC 5000 here significantly. And then the second goal of the CH4 is we really want to improve the performance of multi-threaded MPI communication. As has been multi-core system become dominant in supercomputing world, we really want to identify what was the cause of the performance degradation in multi-threaded MPI communication, and what we can do about it. So in CH4, we have introduced multiple optimizations in how to map the traffics through different different network communication contexts, and so that they don't have to compete for the same log when communication. That greatly improves the performance as well, as you can see the bottom right figure here. So basically, we're with multiple communicator between two processes, we'll be able to map the traffic to different hardware communication contexts, and by doing that, we're essentially with multi-thread MPI operation, we'll be able to achieve a similar message rate compared to the MPI thread single case, which multi-thread is not enabled. And the last big point of CH4 is the support of GPU, which is what I'm going to talk about next. So next slide, please. So this is just an overview of what CH4, what the layers and structures inside the MPICH today. So we have the MPI interface that deal with the application, but below that we have the MPI layer, which provides the communicator management, group management, and we have also the implementation of machine-independent collectives and data type management. And below that is what we call the abstract device interface, which essentially is the interface internally in the MPICH library that handles for that. The interface is the device related operations with the MPI layer. So we have the legacy CH3 device, and the CH4 has a lot of components, as you can see. but if you look closely, we have these NAT mods and SHMAN mods, which are targeted support for network communication and shared memory communication via OFI UCX or using SQMM, and also we have GPU IPC in there. So this is just a rough idea of our structure. Next slide, please. So as I mentioned, since GPU has been an important architecture in the supercomputing world, we really want to have a good support for in MPICH for communication using GPU buffer. So in this case, we're actually targeting multiple different kind of communication, right? We have communication between the GPU, between two GPUs over the network, or GPUs between GPU and CPU and main memory over network. Or in the third case, we also want to look at the case when two GPUs on the same node but maybe belong to different processes and they want to talk to each other, and how that communication can be supported and in an efficient way. So next, please. So the first step is basically we want to support data movement between GPU buffers. So this is basically largely relies on low-level libraries like libfabrics and UCX. So whenever a GPU direct RDMA or equivalent technology in different vendors' hardware is supported, we would have our communication using GPU buffer address directly. Okay, so that's essentially the fast pass. It just passes the pointer. But in the case when the GPU direct RDMA is not supported, or in some cases if the data type is too complex and is not supported for native GPU data movement, we have a fallback path that relies on unpacking and using the active message path to handle this in this scenario. Okay, so this is by adding this functionality, we're essentially providing the support of how to move data to and from GPU buffers, and the destination is regardless what the destination is and regardless what the data type is. And next slide, please. And then in order to efficiently support the different data type, which is, as you may or may already know, is a big feature of MPI. We have basically what MPI allows is the user can create arbitrarily different shape of data type with different data structure, contiguous, non-contiguous, and with different structures. So in order to, some of them have direct support by the network library in communication, but a lot of them, which maybe rarely used, but we have to handle the GPU support for these cases. And what we introduce is a new data type handling engine called Yaksa. Essentially, is it's a similar, if you would, it's kind of similar to the design of the fabric, where we have a data type front end that deals with the different data types and functionalities, but we have several different backends, including a CPU backend, a CUDA backend, a HIP backend, and Z backend for different GPU vendors. And what these backend provides is they not only have the support of packing and unpacking GPU, it also contains GPU kernels that can efficiently do this packing and unpacking using GPU instead of like just move data between the CPU and GPU. As you can see, the performance of using GPU-based packing is significantly higher than using the host memory due to the high memory bandwidth. Next, please. Okay. Lastly, this is especially for communicating between two GPUs on that share the same node. Okay. So so between two GPUs on the shared node, they may not have a high bandwidth connections, something like NVLink. So what we're trying to do here is, in case if we are dealing with the communication between two GPUs on the same node, we're trying to use GPU IPC to for large data transfer. Essentially, what it does is, for the sender, it will create an IPC handle, and instead of sending the entire data over shared memory, it will just send that handle to the target process. So the target process can look at that handle and see, oh, there's a data on that GPU, and I could initiate a read, or I could let a sender to initiate a write between the two GPUs, so they can benefit from this high bandwidth link between the two GPUs. This is more of a work in progress. We have a initial implementation on this, but we're currently looking at different cases where what might be the threshold for doing GPU IPC versus traditional shared memory communication, and this is especially related to the cost of creating IPC handle and transmitting them, and this operational overhead versus the benefit of the high bandwidth transmission. And another set of investigation that we're looking at is how, in this case with GPU IPC, how do we support non-contiguous data type? Because in that sense, we to do GPU IPC, we'll also have to transmit the description of the data type itself, which adds more overhead, and we would like to understand in what circumstances this could be beneficial, so we can include them. But this is basically all the current status of GPU communication support in MPICH today, and this work has been done in close collaboration with our vendor partners, including Intel, Cray, AMD, Manos, and NVIDIA. Next slide, please. This is a little bit more than just the GPU communication support. This is more of a future direction that we're working on. So previous support is mainly on communication, but as many of you already know, that synchronization and communication with GPU today can be quite expensive. So what happens is, a lot of this MPI communication is controlled by CPU, although the GPU buffer can be directly talking to the network card. But we still need CPU's involvement to handling all the MPI related stuff. That essentially forces the synchronization between the GPU and CPU in order to do the communication, which is pretty expensive due to the kernel launching, and essentially it's just bad for the GPU program model. So there are several solutions that we're looking at, and the MPI standard forum is looking at. So one is this partition communication, which introduced new interfaces that we can indicating whether communication is ready for transmission, or is there a data arrive for receive operation. So that sense. So in that case, as you can imagine that as this is, the CPU could be preparing the necessary data structure and information for the communication, and the GPU could at one point say the data is ready, and you can start the communication. So in that case, the GPU could be controlling the timing of the transmission without forced synchronization between the CPU and the GPU. So stream triggered operation is kind of similar, the kind of similar idea, but we're basically doing a prototype and trying to have some rudimentary implementation using signals. instead of having the kernel to be to finish and synchronize between GPU and CPU. And lastly, we were also thinking about maybe we can just pass the GPU stream as a parameter into MPI operation, or as a hint in through the MPI hint, so that the library inside can be aware of that. This is a GPU operation, and we need to take a special path for that. But this is largely a work in progress, and hopefully we'll have something more concrete and that we can showcase later this year. Next slide, please. Okay, so apart from the GPU support, there's another thing that's related to our usage with usage of the fabric that I want to talk about is the new collective infrastructure. This is largely Intel's work and Intel's contribution into the MPICH code. What it does, it creates a template like structures for anyone to create new collective algorithms for the MPI collective operation. So there are already multiple different algorithms existing in MPICH today that is generic to all different kind of hardware. But this infrastructure also adds support for device level for hardware accelerated collective support, including using the triggered operation by OFI or HCall in UCX. Next slide, please. And apart from the collective algorithm infrastructure, there's also this a collective selection logic that can be customized by the user. What it needs is essentially the library would read a configuration of a JSON file. What the JSON file describes is in different circumstances, for example, with different communicator size and message size, or support availability of hardware collective support. These are the threshold, and based on this threshold and what kind of collective algorithm should be used in this case. So this can be customized by if the user have expert knowledge of how their machine works and how certain algorithm can benefit can be beneficial for their application or for their machine, and the user can do that. Or there's there could be external library tools that profiles an application that does that, and your vendor partner could also be telling you that, oh, we have this machine and we have this configuration that you should use to get the best performance out of it. So essentially there's all kind of different sources that can provide you with this configuration. But what the selection the collective selection framework does is we provide this this format of JSON, and we'll be able to understand these decision criteria and reconfigure the collective system based on that. So this is like the collective algorithm framework. This is also contributed by Intel. That's next slide, please. Yeah. Okay, so that's pretty much the state of art today. So so since version 3.4 has been stable and released, our work has moved on to the 4.0 series. As I mentioned, the alpha 1 release is already out there, and we hope to get the GA release sometimes next year. But and in between, we'll have multiple beta release hopefully. So the biggest focus on this one is basically the MPI4 support, as the forum is close to rectify the MPI4 standard, and we're aiming to have a release ready for that when that is come. And also some of the work in progress that can come into the 4.0 series are including improvement on collective with GPU buffers that we have multiple works on related, including using GPUs for reduction operations and whatnot. And there will be more being included in this 4.0 series, and that's pretty much all I have today. And thanks everyone. And I can take questions if there's any. Thank you.
Any questions for the speaker? Thanks, Charles, for that fun fact. I think everyone's seeing the IM message.
Yeah, I saw that. It's next summer. It's next summer. That's a typo. We hope the GA is coming out next summer, but we'll have a release whenever the MPI4 standard is rectified, and that will contain all the functionality. You know, just might be a beta release, but then the last mile will be bug fixings and making it really stable and be useful for our partners and users.
All right, any other questions? Okay, if no other questions, I'm going to let Yanfei
All right, thanks everyone.
thank him for his time here.